Hello everyone. Our group is composed of myself, Bharat, Dylan, Jack, and Leonie, and we are going to present the paper Risk Prediction in the Life Insurance Industry using Supervised Learning Algorithms. In this paper, the authors have applied machine learning algorithms for classification tasks to classify risk levels for life insurance applications. We will start with an introduction to the industry and the classification problem that the authors are addressing via their work, cover exploratory data analysis, data pre-processing, results of machine learning algorithms, namely multiple linear regression, neural networks, random tree, and red tree, and then conclude with a note about further work that can be done in this area. We now move on to the introductory slide. It is extremely important for a life insurance company to assess the risk of an applicant accurately in order to make sure that applications with an actual low risk are accepted and an actual high risk are rejected. Otherwise, a high number of individuals with an unacceptably high risk profile will be issued policies, and when their nominees file for claims, the company will face huge losses due to a high rate of payouts. Such a situation is called adverse selection, where individuals who are most likely to suffer losses take insurance and those who are not do not, thus resulting in a financially unsustainable situation for a company. Traditionally, the process of underwriting has been done using actuarial calculations. Actuaries group customers according to their estimated levels of risk determined from historical data. However, these conventional techniques are time consuming and it's not uncommon to take a month to issue a policy. They are expensive as well, as a lot of manual processes need to be executed. Predictive analytics has emerged as a powerful tool to streamline the underwriting process to reduce the time of policy issuance and to improve the accuracy of risk prediction. In this paper, the authors use data from Prudential Life Insurance Company and investigate the most appropriate data extraction method and the most appropriate algorithms to assess risk. The authors have applied data analytics to the Prudential Life Insurance data, which is a publicly available data set. It has 59,381 applications with 128 attributes, which describe the characteristics of life insurance applicants. The attributes include categorical as well as numerical variables. They belong to four broad categories: health and medical history, employment and financial history, insurance history, and product information. The objective is to use these attributes to come up with a model that can predict the risk rating of an individual on a scale of 1 to 9, where 1 is the smallest and 9 is the largest risk profile. This rating will then be used to make accept or reject decisions about policy application and to price policies. We now move on to data analytics pipeline that the authors have followed in this work. The authors take the initial tabular data and perform EDA on it. Questions like whether the age and risk level of an applicant are correlated or what is the BMI distribution of people with a particular risk rating can be answered via EDA. Daniel will discuss EDA in greater detail. After this, the dimensionality of the data is reduced through two techniques: principal component analysis and correlation-based feature selection. Data with these reduced features are then subjected to 10-fold cross-validation so that the trained model generalizes well. The trained data is now fed to multiple linear regression, neural networks, random forest, and Z-tree algorithms to generate predictive models. The predictive power of these models is then compared using error measures like MAE and RMSE to select the best model for the risk prediction task. Dylan will now cover EDA.
Thanks, Barrett. For a dataset, exploratory data analysis, also known as EDA, is designed to understand its main characteristics via visualization. It provides tools and insights for us to develop an appropriate model. Time is limited in this paper presentation, but because of the imperativeness, a relatively small yet representative portion of EDA is introduced here. Let us first look at four continuous independent variables in the dataset. They are namely age, height, weight, and body mass index, aka BMI of insurers. All of them are normalized. According to the histogram, age and BMI are roughly symmetric, while height and weight are respectively negative and positive skewed. Also, BMI has heavier tails than age. Most categorical variables of our interest have 2 or 3 different levels. For example, the bar chart on the right depicts insurance history 1. Over 2/3 records are labeled as level 2. However, there are 3 special categorical variables. Insured info 3, with 11 levels possibly indicating insurer's nationality, presented in the left bar chart. Employment info 2, with 38 levels probably distinguishing insurer's professions. And medical history 2, with 648 levels perhaps denoting different diseases. The response variable for this study is ordinal with 8 levels, with the highest frequency in level 8 and lowest in level 3. This targeted variable is related to the final decision associated with insurance application. Using all 4 continuous variables and the response variable for multinomial logistic regression, computed significance level indicate that all 4 variables are statistically significant, despite a few weird-looking p-values in red. Now Leonie will cover the data pre-processing part.
The general goal of data pre-processing is to remove noise and outliers in the dataset. The dataset has 59,381 instances and 128 attributes. Our goal is to first detect the missing values in the dataset and impute them based on their missing mechanism. Second, reduce the dimensionality of features that will be later used in the models. First, variables with more than 30% missing data were dropped. Therefore, only 4 variables, employment info 1, 4, 6, and medical history 1 need to be imputed. Next, we need to determine the missing mechanism of this missing data. There are 3 kinds of missing mechanism: missing completely at random, missing at random, and missing not at random. The Little's test indicates the missing data is not missing completely at random, so it can only be either missing at random or missing not at random. And from the missing value plot on the right, we can see there is no clear pattern of the missing data. Therefore, we assume that the missing data is missing at random. With this assumption, the missing values were imputed with multiple imputation by mice in R. Next, we're going to talk about dimensionality reduction. The first question is, why do we need to reduce the dimensionality? The reason is there are 117 features available in the dataset, but not each of them contributes much to the variation of the response variable. So we only want to keep the features that influence the response variable the most, and thus we need to reduce the dimensionality of the data. In this way, the prediction power can be much improved. There are 2 ways to reduce the dimensions: feature selection by CFS, or correlation-based feature selection, and feature extraction by PCA, principal component analysis. So in this study, both methods were used. CFS was done by selecting a subset of the most correlated features with a response variable, whereas PCA was done by creating new attributes by combining the existing features. A rank was also provided based on how much variation each attribute contributes to the response variable. So the result is, by CFS, 33 variables were selected out of a total of 117 features. By PCA, 20 variables were extracted based on a threshold of 0.5. With the reduced features, we can now proceed to the data modeling section.
Now I'm going to cover the algorithms they used to train models and perform the analysis. The first model they used is multiple linear regression model, which is a simple method to train and fit models, and they went over a model selection process to find the best model by looking at variance significance of each variable. Additionally, the sum squared error of the distance between the data points and the observed values is the main source of error wanted to be minimized. Therefore, they chose a model which would produce the minimum sum squared error to do predictions. This model did particularly well in the principal component analysis case, provided the minimum mean absolute error, and root mean squared error compared with other attempted models. Next, the researchers used two types of decision tree algorithms, which are random tree and rep tree, to do predictions. Rep tree makes use of regression tree logic to create trees in different iterations, and it develops its model by information gain and variance deduction. By bias-variance trade-off, rep tree tends to produce a simple model with large bias but small variance compared with other decision tree methods. Random tree, however, focusing on estimating class probabilities and selecting a subset of attributes randomly to train and fit models. The performance of random tree is not as well as other attempted models, producing the largest mean absolute error and root mean squared error in both PCA and CFS cases. The author noted that the random tree method is efficient when the dataset is large. Probably the dataset they have is not large enough. In contrast, rep tree did very well in the CFS case, which produced the minimum mean absolute error and the root mean squared error compared with other attempted models. Lastly, artificial neural network is used by the researchers for making predictions, just like what we did in class. The performance of their neural network model, however, did not provide a minimum value in any types of the errors compared with other attempted models. Therefore, the data analytical solution is much easier to do compared with actuarial algorithms. But looking at the minimum mean absolute error and the root mean squared error provided by all four models, it is obvious that the machine learning algorithms can provide good predictions in insurance data. However, the researchers neither provided anything about the structures of their models, nor did they provide the package they used in R. Noted that different packages may have different performance while making predictions.
Now, to summarize the work, the authors use CFS and PCA to reduce the dimensionality of the data to determine variables that most explain the target variable. CFS had a greater explaining power than PCA as the original attributes were not transformed. In terms of accuracy measures, the REPT algorithm had the highest accuracy with the lowest MAE and RMSE statistics of 1.53 and 2.03 respectively for CFS. Multiple linear regression showed the best performance with MAE and RMSE values of 1.64 and 2.06 respectively for PCA. Future work can focus on clustering applicants based on their attributes. Such work can be performed using unsupervised machine learning algorithms. Such clustering can help companies understand which features make applicants most or least similar and can help in future customer acquisition strategies. We can also use smaller data sets but with more attributes to using techniques such as few shot or one shot learning to investigate the effect of these additional attributes on prediction accuracy. We now conclude our talk and are happy to take any questions. Thank you very much.